Okay. So I think we can start for this second part of the morning. So we have here now for the next talk Mario Polino. He is the head of the cybersecurity and IT at Leaf Space. And he will give us a talk entitled the Space Race Condition. So welcome, and the floor is yours.
Okay. Use this mic?
And use this one. Yeah. Very good. It's okay.
Okay. Okay, I need to unlock my computer. Hello, everybody. I'm Mario. Thank you for coming to this talk. I'm gonna talk about race condition. Okay. Space here is here because we like space, so we like the context, and it was a very nice title to have space race, but it's race condition. Okay. So that's what I'm gonna talk about mostly. Race condition per se are vulnerability that arise in special condition that are basically when you have a concurrent system and a shared resource. Okay, and the reason why I like them because they are hard to spot, hard to debug, hard to fix, and they are very impactful. Okay, so after you've finished looking for buffer overflow, SQL injection, bad authentication in your system, this is the next thing you want to look for, okay? It's hard to spot them because there is not a clear pattern. I mean, there are some pattern, okay? But why we have tools to spot some of the other, I'll tell you, the tooling for this type of vulnerability is way less present, but the impact that they have usually is way bigger than other vulnerabilities. Okay, and the reason of that is because they are usually kind of logical vulnerabilities. They are intrinsic to the problem that your program is solving. Okay, so we are talking about vulnerability in the code. So one thing before start discussing the vulnerability per se and how it works, I want to talk with you is the difference that you have between concurrency and parallelism. Okay, they are similar word in some contexts they are synonym. Okay, but when you are looking at the code, they are very different thing. Okay, parallelism is when you have two things that are running at the same time. Okay, so you have two CPU and the code is running on those two CPU. Okay. Concurrency instead means that you have maybe you have one single resource, one single CPU, but the CPU is switching between one task and another. From the user perspective, from the use of the system, it looks like there is parallelism in this case. But the reality is there is no parallelism here. It's just switching context between one task and another. Okay? Race condition exists when you have concurrency. Okay? It looks like parallelism, but actually, this is where they are easier to be exploited. Okay? You have one single CPU and the task is switching. They are still present when there are parallel things. Okay? But best case is for an attacker. Best case for an attacker is concurrency. Okay. So to give you an understanding of what is it, I'm gonna do an example with value. Okay, value is money. Okay, so the classic example is bank transfer from A to B. Okay, so there is one guy I want to transfer 800 euros to someone else. So as a developer, I need to build the code that allows that. Okay. So let me show you some pseudocode that I have here. So this is a possible implementation of transfer money from A to B. Okay? So what I do, I retrieve the current amount of money for account A. Okay? I check that you have enough money for the transfer, so more than 800. Then I compute the new amount for A. I got all the amount. I removed the amount that I want to transfer. I build the new value for amount B. So I get the value of B. I add the value there. And then I store the two new value in account B and account A. Okay? If you look at this code as it is, it's not vulnerable. At least I don't see vulnerability. If you spot one, tell me. Okay? It looks sane. You go through this. Logically, it's sound. If you run it multiple times, that sounds good. Okay? The point is, if you run this in a concurrent system, that's broken. Okay? And what is a concurrent system, for example, for a bank application, if you have multiple people doing multiple transfer at the same time, okay? You go through load balancer, multiple server, and database, okay? The concurrency, where is the concurrency in a system like that is that you can have two transfer happening at the same time, okay? So if we look at the system, okay, we have two transfer going at the same time. Let's say that A is sending 800 euros from A to B, and A is sending 800 euros from A to C. So same transaction from A to B and A to C. The code is the same. Okay, the only difference here is I'm sending money to C instead of B. So I'm running this on a concurrent system, single CPU. That's different from my slide. Okay, it's back. Thank you. So I want to run this on a concurrent system. It means I have eventually a single CPU, okay, that needs to run this. But from a user perspective, I want the transfer to happen in parallel in the sense that I don't need to wait the finish of the first one to handle the second one, okay? The system per se to user is parallel. Anyone can show up and do the transfer when they want, okay? What happened in the system that can run one single instruction at a time is that either I'm running the first one or the second one, okay? So what happened is that I need to schedule basically the instruction in my resource. This is a way to schedule the first transaction and then the second one, but there are any possibility. I can run the first one, then run the second one, and then go back to the rest of the first transaction, or in between, okay? And which one is run on where? It's up to the scheduler. What the scheduler is doing, nobody knows, usually, okay? I'm joking, but the scheduler is taking decisions that do not depend on user level, okay? So let's have a look at this scheduling, okay? Let's assume this is the scheduling that happened during our execution, and let's try to see the value, okay? And how the value and how the results are at the end, okay? So let's say that A has 900 euros at the beginning in the account, B and C have nothing, okay? So you read the value from A here, then you go on the other transaction, you read the value from A. So the read is 900 on both sides, okay? Then you go back here, you check, is amount greater than 900? It is, I read 900. And then I go there. Is this greater than 900? It is. And then I start executing this. So new amount A is 900 minus 800, 100. New amount C is going to be 0 plus 800. Okay? Then I switch back, and I start executing this. How much? Amount is still 900. So it's going to be, amount A is going to be 900 minus 800, 100. And amount B is going to be 0 plus 800. Okay? Then I store here, I store there. What is the result? A is going to be 100. B is going to be 800. C is going to be 800. Okay? So if we sum up the number, we just created 800 euros. Okay? That's good if you are A, B, or C. That's bad if you are the bank actually handling this. Okay? And why this happens? This happens because I had this specific scheduling on my transaction. not because the code has a vulnerability per se. Okay? The code, if you look it from a single perspective, from a single execution perspective, it's safe. The reason why you get this problem is because I am in a concurrency system where the scheduling is not up to me. It's up to another part of the system. Okay? And you can use this in many things. Okay? Classic use of this is filter bypassing. You have a rate limit. Okay? You have distributed system that is limiting, and the system is distributed geographically. Okay? How you update everything. That's complicated. And there are famous cases where this has been used to literally create money. Okay? This is a blog post a few years ago where a guy used a Starbucks gift card, okay, to do exactly what I showed you. Okay? I mean, they fixed it. It's been a while. But money doesn't mean SEPA transfer. I think hopefully that thing is safe. Okay? But it can be something else. That can be it can be a side system, but the result at the end is that you can buy coffee with that. Okay, so this is one example I wanted to show you. What is the problem in this example? Okay, the problem is that we have a shared state, okay, and we have multiple tasks that are writing the shared state. Okay, if you are just reading, if everybody's just reading, that's not a real issue. The problem arises when, I mean, the state needs to be shared, okay? And the writing, and you need multiple writers, or at least one writer, because the other is reading a wrong value, okay? What is the shared state? It can be literally anything where you store state. It can be a database, like in this case, where you access a database. It can be shared memory for multiple processes. It can be the file system of your thing, okay? It can be, for example, like signals and triggering signals in a process, okay? So what is the shared state? It depends on the system. And it's not like just something that it works on web vulnerability, it works at any level, okay? So let me give you another example that is more useful for what we do. Firmware upgrade, okay? This is an example of firmware upgrade. This is real code. I think you can execute it. So what this upgrade is doing, I want to do a firmware upgrade verifying the signature of the firmware. Okay? So I receive the new image firmware. I receive the new signature. Okay? I save it in a file. And then I verify the signature. If the signature is wrong, abort. I do not do anything. If the signature is OK, I actually do the update. OK? Same thing. This sounds good. OK? What is actually happening? So this is the timeline. I upload a firmware. I do signature verification. I do firmware upgrade. OK? And I'm writing on a file. What happens if, while doing this process, I'm going to upload another file? Because how this is done, I'm writing on the same file here. Okay? If I do another request at the same time, I actually have a pointer. If I do another request at the same time, this is going to arrive at some point and overwrite whatever file was there. Okay? So if this arrives at this point, when I do signature verification, that will fail because I changed the old firmware. But if the new firmware, so this is the failing, if the new firmware arrives later, after the signature verification, what happens is that I already done the verification, I change the file, and the file that I'm reading after is the one that is actually updated. Okay? And this comes from real vulnerability. So there are multiple CVE on firmware upgrade where the upgrade is done like that. Okay? Where you can upload and not sign the firmware because you are skipping the validation. or actually you are using a real firmware to validate, and then change the firmware after the validation. Okay? This type of vulnerability is known as time of check, time of use. When I'm checking, I have something. When I'm using, it's changed. Okay? The thing when I check, the time of check is different from the thing that I actually use. Okay? So how I fix this? Okay? Because that's our problem. How I fix this? One fix is I don't have a shared state. Okay? I try to not have a shared state. In my case, the shared state was the file, right? The reason why this happened is because I'm writing on the same file. So I'm changing the resource, the state. If I randomize the file, then when I'm using the firmware, I'm using the old one. If I'm uploading a new firmware, the name is changed. Okay? This works, but it's limited. Then the security of your system rely on the randomness that you have here. Okay? If I can guess the file, if I can synchronize somehow the generation of the name of the file, then I'm good. No? And this is the case where you have the two file resources. There is a better fix for that. That is to avoid time of check, time of use. What I'm using needs to be what I'm checking. Okay? So if you change your code, okay, instead of checking the file and then using the file, what you do, you load the file in memory, you check it, and then you use what you already loaded. Okay, let me show this that is better. The idea is when I'm doing the firmware upgrade, instead of reading again the file from the file system, I'm using the one that I already read and validated. I'm never gonna go through the file system anymore. I'm uploading that. I'm upgrading that. Okay? This way we removed the difference in time of check, time of use. Okay? And if someone is arriving before the signature, both upgrade will fail. If someone is arrived after, this file is gonna be read by another process. Okay? So the two options that you have is either split the state, I have two different states, or what I'm checking is what I'm actually using. But that's not trivial. Sometimes it's hard to identify those spots in a system. This part here, that's the vulnerable time. That's what is called the race window. It's the time that I have to actually change whatever is there, okay? And if I'm able to hit that time, I'm winning the race, okay, as an attacker, because this is the race window. The size of this impact how, as an attacker, how likely is that I'm gonna succeed in the attack or not, okay? And this is the nice thing. I can control that window, okay, depending on the system. There are many stuff that you can do so that you can time the arriving of the second system, okay? Besides like spamming your request a lot, at some point will happen, okay? Even if it's unlikely, at some point will happen. You can preload a lot of stuff so that it arrives more or less when you want. I can try to control the window size. Okay, if there is some processing going there, sending a bigger file will slow down the process and increase the window. And I mean, for HTTP and other stuff, there are techniques that you can use in the network system to actually synchronize your attack. Okay, there are a few famous things. One is called last byte sync. Okay. What is the idea? The idea is that if you're doing a request, for example, an HTTP request, you send the whole packet, but the last one, you hold the last byte. The system is waiting for the last byte, and is going to process the entire request only when you receive the last byte. Okay? And because you can hold 1 byte, you can try to send it later. For example, what you do is you send a valid firmware, but the last byte. Then you send the wrong firmware, but the last byte. And then you send the 2 last bytes close together. Okay? So that you know the 2 things will be processed more or less at the same time. Okay? There are the fancy version specific for HTTP2, where you can send multiple packets, multiple stuff on the same connection. Okay? So it's basically a fancier version of that. Or you can use low-level networking stuff, like TCP frame. Okay? TCP frame are ordered. You hold the first one. You send it as last one, because the arriving of the frame, it's random, but you can control that. So that first you load the entire firmware in memory, and then you trigger it with the last frame when you want. Okay? And then depending on the network and the system that you have, you can spot other way to actually synchronize the attack to hit the window. You use that, you try a lot of time, you get the attack. Okay? I show you stuff high level. Okay? This stuff exists at any level. Okay? If you write C code and you have shared memory, okay? If you write kernel driver, then the syscall can arrive multiple times. You have signals that can interrupt your system. So the concurrency in the system that we use is basically everywhere. Okay? It's not that, okay, it's a kernel driver, I'm safe. No, actually, most of the vulnerability that people find in the kernel are race condition nowadays. Okay? Because you write your driver, and you don't consider everything else that is around your driver. And your driver is safe if you look at the driver per se. And an example I want to bring that is, when you're trying, so how you solve this, usually you use mutex, okay, to synchronize your process, okay? But even CPU are concurrent, they switch. This means that that thing that I show you, that where you switch from one task to another, from loading the value of the database to another, okay, this is true at instruction level for CPU. The CPU can switch context at any time. So when you execute assembly code, I'm switching from one to another, accessing the memory in multi-thread. Okay, that's a concurrent system on memory, and you use mutex to do that. But then the next question is how you implement mutex if the switch is changing from one point to another. You need to do it carefully with some specific instruction that are usually called atomic instruction. Those are instructions that you know they cannot be interrupted by the CPU. Okay? The example in x86 is the exchange value. You need to use that instruction to exchange the value. You cannot read one value and update the value. Right? If you read and write at the instruction level, you have a race condition there already. So that stuff, don't use this code. I don't know if it's safe, right? But the point is, even at the instruction level, you have that problem. Implementing is not trivial at all. You need to use specific instruction, and this depends on the architecture that you are using, okay? And which instruction allow you to do that. There is some attempt from academia to try to solve the problem. There are tools that have been built to try to spot this type of vulnerability, okay? But it's still an open problem, okay? We don't have a tool that says, oh, I'm going to run my code through the tool and it's going to tell me if there is something that is a race condition or not. And the hard part of this is because it deeply depends on the context, right? And on the logic of your system. So the best thing that you have is, when you write the code, try to not put it there. or if you can invent a new system, then we are all happy to have a way to spot them. Few things to take away. So if you have concurrency, you have race condition, and you have concurrency. Unless very specific system, you have concurrency nowadays. It happens at any level, web application or instruction level. The problem is the same, the fact that you are switching context. And we are doing it at any level. Not because we are parallel, but because we are concurrent. We are executing stuff at the same time. One option is to not have unsafe state, but it's really hard. So the other option that we have right now is to avoid to write vulnerable code. And that's a bad advice. It's impossible to write a non-vulnerable code. But it's an open problem. It's still a problem that we have nowadays. So that's it. If you have any question, I'm very glad to take it.
Thank you a lot. Thank you. So, do we have questions? Otherwise, I start with the first one. So, in the space industry, especially on satellites, but on the ground too, we work with quite a lot of embedded system. And sometimes the only way to develop is on a simulated environment. And these simulators are not always perfect. So what is your advice in order to minimize this kind of problem when, in addition to all the bad things that you showed in your presentation, you are also working on an imperfect simulator?
One way is to try to think of your state and have a consistent state in every step. So the example that I've done with the bank system where you upgrade one value and another, okay? Basically, you have an inconsistent state in the transition from one state to another. There is at some moment in memory, actually there are more money because I'm doing the computation. If you have a way to avoid that, so you do the computation in a way that it's always consistent, then you don't have a race condition. Can you do that? It depends on the problem. Sometimes you can, sometimes not.
Understood. Do we have other questions from the audience? Okay. But if it's not the case, then I thank you a lot for your presentation. Thank you one more time, Mario.